Ever wonder why you don't get charged like 10 bucks every time you ask an AI to write an email? Well, today in this explainer, we're popping the hood to uncover the engineering magic that makes large language models fast, scalable, and economically viable. The real secret to handling millions of daily conversations isn't actually just about the training. It really comes down to inference engineering. It's this fascinating world of squeezing every last drop of performance out of our hardware, and today we're breaking down exactly how it all works. We've got a lot of exciting ground to cover today. We'll look at the LLM inference bottleneck, conquering the KV cache, keeping the GPUs busy, shrinking and splitting models, and finally, the inference engine ecosystem. Let's dive in.
All right, part one, the LLM inference bottleneck.
So, why is running an LLM actually so demanding? Well, it's basically a massive memory management problem. When you load up, say, a 13 billion parameter model, boom, about 65% of your GPU memory is instantly eaten up by the static model weights. And that memory, it's completely locked in. But the rest of it, which is often 30% or more, is consumed by the dynamic state of user requests. The model itself stays exactly the same, but the context of those ongoing conversations grows and shrinks totally unpredictably. And honestly, that's where the chaos lives. This dynamic memory is primarily what we call the KV, or key value cache. As the GPU generates words one by one, it acts like this hungry beast, right? And the KV cache feeds it past context, so it doesn't have to recompute the whole sentence every single time. But here's the catch. Because we have literally no idea how long a user's prompt or the AI's response is going to be, traditional systems just pre-allocate these massive chunks of continuous memory, just in case. It's incredibly inefficient. It causes fragmentation that can actually waste up to 80% of your available space. Crazy, right? Section 2. Conquering the KV cache. Now, what's really amazing here is how a classic 1970s operating system concept literally swoops in to save the day. It's called page detention. Instead of forcing a sequence's KV cache into one giant clunky block, page detention divides it into fixed-size pages. It's exactly like virtual memory in classic computers. You only allocate a new page when you actually need it. This incredibly elegant trick allows systems like VLLM to eliminate fragmentation entirely, dropping that memory waste from a staggering 80% down to under 4%. But you might be wondering, how big should these pages actually be? Well, if your memory blocks are too small, the system just completely drowns in overhead trying to manage them all. But as you increase that block size, moving along the x-axis here, the time it takes to swap memory drops dramatically before finally leveling off. So choosing the right block size is a total balancing act. Notice that sweet spot right there in the middle, between 16 and 64. That is exactly where latency per token flatlines near zero, giving you basically perfect memory efficiency. By figuring this out, VLLM can cram vastly more concurrent requests into the exact same GPU, improving overall throughput by up to 4 times compared to older setups. Okay, moving on to section 3, keeping the GPUs busy. Once your memory is finally sorted out, your very next job is scheduling. Think of older static batching like waiting for a whole table at a restaurant to finish eating before you seat anyone else. If just one person eats slowly, the entire table is blocked. Continuous batching, or dynamic batching, completely flips this. It seats a new guest the exact second a chair opens up, interleaving those requests token by token on the fly. The whole process operates in this beautifully simple loop. First, you generate a token for the running sequences. Then, the millisecond a sequence finishes, you evict it. Next, you instantly schedule and insert a new incoming request right into that newly freed slot. By operating at this granular token level, you can push your server's throughput in order of magnitude higher, and you do it without any latency penalty. It's brilliant. We also have to keep the GPU busy at the micro level, and we do that using operator fusion. Normally, a GPU reads data from memory, does some math, writes it back, and then reads it all over again for the next step. It's a lot of wasted travel time. Operator fusion fixes this by combining multiple, separate operations into a single GPU command. This saves the GPU from making costly, redundant trips to global memory, letting it rely on the super-fast SRAM right on the chip instead. It keeps the compute engine just blazing fast. Section 4. Shrinking and splitting models. So we've solved memory and scheduling, but we still face the ultimate hardware question. What if you have an 80 gigabyte GPU, but a 70 billion parameter model needs like 140 gigabytes just to load? When the model itself is fundamentally too big for the physical hardware, we have to rely on reduced precision and some very clever distribution. First up, we shrink it down using quantization. Instead of using highly detailed 16-bit numbers for the model's weights, we basically compress them into 8-bit or even 4-bit integers. It's exactly like lowering the resolution of an image, you know? You lose a tiny, often imperceptible bit of detail, but the file size just plummets. This is the exact magic that allows you to run these massive models right on your local laptop or consumer hardware. Now, when shrinking just isn't enough, we have to split the model across multiple GPUs. We can either split the math within the layers themselves using tensor parallelism, where multiple GPUs crunch the exact same matrix multiplications simultaneously, or we can use pipeline parallelism, passing data sequentially. So GPU 1 handles layers 1 through 10, passes the baton to GPU 2 for layers 11 through 20, and so on right down the chain. Finally, Section 5, the inference engine ecosystem. So how do you actually use all these brilliant techniques? Well, the open source community has packaged them into some incredible ready-to-use engines. If we look at the heavy hitters here, VLLM is your absolute go-to for high-throughput cloud servers, mainly thanks to page detention. Then you've got TensorRT LLM, built by NVIDIA, which aggressively uses operator fusion to maximize raw speed on their specific chips. And of course, Llama.cpp, which famously brought LLMs to edge devices and laptops using intense 4-bit quantization and that portable GGUF format. There are also highly specialized tools out there, like cTranslate2. What makes this engine so fantastic is its pure adaptability. It features automatic CPU code dispatch, meaning it actually detects your exact hardware on the fly and selects the absolute most optimized backend, whether that's Intel or Apple. By seamlessly handling reduced precision and dynamic memory caching, it's essentially an incredibly versatile Swiss Army knife for production environments. We've seen how quantization, smart batching, and brilliant memory management make today's AI possible. But given that paging from classic 1970s operating systems just completely revolutionized AI serving via page detention, it really leaves you wondering, what old trick is going to solve our next trillion parameter bottleneck? The history of computer science is clearly holding the keys to the very future of AI. Thank you so much for joining me on this explainer, and keep exploring.